Alright, so in 2.8 we finally nailed down what the first derivative is. It's simply the same thing as we had in 2.7. Instead of using a, we use x, and we call it f prime of x instead of f prime of a. And from here on out we exclusively do derivatives using this difference quotient idea. Now they ask you first, what if you have some function f? What does its derivative look like as a graph? Well, if you look at where the where the function has a tangent line slope of 0 and 0 and close to 0, you would expect the y-coordinate of your first derivative to be 0, 0, and then get close to 0 there. And so here you've got a tangent line with slope that's negative, and so the y values here are negative. Here it's positive, 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 and then 0 again, so here it's positive, 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 and back to 0 again. And then here it's negative slope all the way down, and so you got negative y values here as well. And notice here is your highest value for your first derivative, and this is the steepest positive slope for your original function, and so everything matches up properly. So now here we're taking the first derivative, and we're using the difference quotient with x plus a into x. And so you plug in x plus h into here and multiply it out, and you distribute the negative sign to the second half here. A bunch of stuff will cancel. What's left, you can now you divide an h into what's left. What you have here will now be, you can substitute in 0 for h, and these terms go away, and you just get your first and last term here. On this one, you have to multiply it by its conjugate, top and bottom. When you do, things will cancel. Then you finally cancel an h, and then you can finally plug in 0 for h, and you get your answer for the derivative. They also ask you to find the domain as well. Alright, this one's a fractional function. So you're plugging in x plus h into the numerator denominator and just x into the numerator denominator. Here, to clear out these fractions, I multiply by the common denominator. So when you multiply these two times this, your denominator and this one go away. You just get the second guy times the numerator. And then here your denominator along with that second term go away, and so this guy times the numerator is the second part. When you multiply everything out, a whole bunch of stuff cancels. You can factor out a h out of what's left, and you get negative 3 on the top, and the bottom no longer goes to 0. You can plug in 0 for h, and you get, this is your derivative. Now they talk about other ways of indicating notation for the first derivative. You can say f prime of x, you can say y prime, you can say dy dx, df dx, d dx of x, d of f of x, and d of x f of x. Those are all different ways to say the exact same thing, that you're taking the derivative. Alright. So a function is differentiable at some point a if the first derivative exists. It is differentiable on an open interval ab if it is differentiable at every number in the interval. So they ask you, where is the function absolute value of x differentiable? Well, they look at positive x equaling positive values, and they find out that it equals 1. They look at for negative values, and they find it equals negative 1. And that makes sense because the slope of a tangent line on this side is going to be negative 1. The slope of the tangent line on this side is going to be positive 1. So you're going to have two different values based on positive or negative x values. At 0, you can't really say anything unless you look at it from the left and the right. And we know from the left and the right we're going to get 1 or minus 1. So the limit does not exist at 0. So we can basically say that this function is differentiable at all values of x except 0. And they even show you what the first derivative looks like. For positive, it's 1. For negatives, it's minus 1. And it's not defined at 0. So you got minus 1, positive 1, and a whole at 0. Okay, so then they give you a theorem that's pretty important. It says if f is differentiable at a, then f is continuous at a. So you can say that. If it's differentiable, then you know it's continuous. Now, if it's continuous, it doesn't necessarily mean that it's differentiable. You can't say that, because you can draw a line here, a curve here, and this is a continuous line because we never lifted our pen off the paper, but we do know it's not differentiable at that corner. There's several ways in which it's not differentiable. If it has a corner, if it's got a break, or if it's got a vertical tangent. And the vertical tangent occurs for cube root of x. If you try and take the first derivative of the cube root of x for a certain value, it does not exist because you get a vertical tangent line. Now if you want to do higher derivatives, for example the second derivative, just take the derivative of the first derivative answer that you got. Just do the same steps all over again. And if you want to find the third derivative, use the second derivative and do the derivative steps all over again. And then you can do it again and again and again. So notice the original function is degree 3. The first derivative is degree 2. Second derivative is degree 1. Third derivative is degree 0. And that's going to happen. When you take derivatives, it knocks it down by 1 degree. That's assuming it's a polynomial. There's other functions where that's not true, like the trig functions that oscillate back and forth between sine and cosine. So let's look at some problems here. They say what's happening, what's f prime at negative 3? So you find negative 1, 2, 3 right here, and you draw yourself a tangent line there, and you can estimate it's probably going to be about negative 1. Then f prime at negative 2 right here, that's 0. F prime at negative 1 right there, well that's a little harder to see, but it's probably about 1/2. And then f prime at 0 right here, it's even steeper, probably 1.5, 3 over 2. E, f prime of 1, okay, that one is 3, it's going up even faster. Then f prime of 2 up here, f prime of 2 is 0. And f prime of 3, right there, that's negative 3 over 2 maybe, thereabouts. Right. So now here they ask you to match up a function with its graph. So you got these a, b, c, d, and you got to match them up with these guys here. If you look at a, this is the original function, and you've got 2 places where you have 0 slope, over here in the minus region and plus region. And the only ones that have 2 places where it has 0 is number 2. So this one has to match up with number 2. B has abrupt lines that only have very specific slopes. So it would have to match up with this one that gives you very specific numbers for your first derivative slopes. C, this one only has 1 place where it has 0 slope, and number 1 only has 1 place where it has 0 slopes, whereas number 3 has 3. This one has 3 places where you have 0 slope, and this one has 3 zeros, so D matches with 3, C matches with 1, and so on. Then they ask you to take the original function and draw its derivative, and you just do what we've been doing. You piece things together as you go along, and you can figure these guys out. If you just do it nice and slowly, you'll be able to figure it out one step at a time. 21. They want you to find the first derivative of this guy. Well, this is a line, and its slope is 3, so you would expect your answer to be 3. So you plug in x plus h into the function minus f of x all over h. Expand out, things cancel. You can cancel an h, you got just a limit of h approaching 0 of 3, and that equals 3, just like we expected. Now this one, when you plug in t plus h in for there, and you plug in t in for there, you drop your brackets, expand everything out, things cancel. Now you can plug in 0 for h and you get your first derivative. On this one you're plugging in x plus h, or just x. You have to multiply by a common denominator to clear out those denominators. A whole bunch of stuff's going to reduce on the top. You're going to be able to cancel one of the h's. Now you can do direct substitution. And when you do that, it simplifies down to this, which you can finally write in this form here, and that is your first derivative. This one, you have to multiply by the conjugate. A bunch of stuff's going to cancel. You can finally do direct substitution. This one, you've got a complex fraction. You clear it out by multiplying by the common denominators. A whole bunch of stuff's going to cancel. Cancel an h, and what's left is your derivative. Question 41. They ask you, state with reasons the numbers at which f is not differentiable. Well, it's not differentiable at minus 4. You have a corner there. It's not differentiable at 0 because it's discontinuous there. 42, it's not differentiable at minus 2 because there's discontinuity there. It's not differentiable at 2 because there's a corner. 43, it's not differentiable at 1 because it's not defined there at 1. It's not differentiable at 5 because you have a vertical tangent at 5. 44, it's not differentiable at minus 2 and at positive 3 because they're corners. It's not differentiable at 1 because there's discontinuity there. Alright, so in this one they ask you to take the first derivative, so you plug in x plus h and then x, and you expand out, simplify, plug in 0 for h, and you get your answer. Then they ask you to find the next derivative, so you use this as your original function, and you take x plus h and then just x, and a whole bunch of stuff cancels and you get 6. And so there's your original function and the first and second derivative. So here they ask you to take the 4 derivatives. So you start out with the original function, plug in x plus h and x, expand everything out, a bunch of stuff cancels, and you get your first derivative. Now you use that one with x plus h and x, expand everything out, things will cancel, you can plug in 0 for h and you get this as your first derivative. Now use this with x plus h and x and expand it out, things will cancel, and plug in 0 for h and you get this as your derivative. And now if you do the derivative of this guy, no matter what you plug into it, you're going to get minus 6 each time, so your numerator is going to be 0. And 0 over h is just 0, and now you can plug in 0 for h, which there was no place to plug it in anymore, and your answer is just going to be 0.